Welcome back to the class. Today we will be seeing about construction, working principle, types and basics of a transformer. Working principle of a transformer. A transformer is a static piece of apparatus by means of which electric power in one circuit is transformed into electric power of the same frequency in another circuit. So, this is the transformer. This transformer has two windings. One is the primary and other one is the secondary. So primary represents one circuit and the secondary represents another one circuit. Here the power input in the primary is being transferred to the secondary without any electrical contact. Here this is being done using mutual flux. Okay. Transformer can raise or lower voltage in a circuit but with a corresponding decrease or increase in current. So transformer will changes the magnitude of voltage or current but the frequency of the voltage or current remains same. The physical basis of a transformer is mutual induction between the two circuits linked by a common magnetic flux. So this is happening because due to the mutual induction and the mutual flux created in the two coils. Okay, if a circuit of a source is being connected in the primary, then this alternating source will produce a induced EMF in the primary conductors, and this primary conductors which produces a flux in the form of pi will link with the secondary conductors. On linking, so this changing flux will create an induced EMF, and this induced EMF when connected to a circuit on the output of the secondary side, then this causes a current to flow through the secondary side. So on this process a mutual flux, that is a secondary EMF, will produce a secondary flux which will again in turn link with the primary. So this causes a mutual flux to be produced, and this mutual flux is produced due to mutual induction principle, and the transformer will transform the power from primary to secondary based on the turns ratio as well as the voltage and current applied within the primary turns. It consists of two inductive coils which are electrically separated but magnetically linked through a path of low reluctance. So a transformer consists of two coils. One is primary coil and another one is secondary coil. These two coils are being uh, electrically isolated but magnetically coupled with the help of the primary flux pi. This flux pi will flow through a low reluctance core, and this is the core of the transformer. These two coils possess high mutual inductance. This is the transformer, and this transformer will possess a very high mutual inductance in such a way that this is the primary coil and this one is the secondary coil, and this flux which is created in primary will be linked with the secondary, and the secondary flux which is induced will be linked back with the primary. So this is known as mutual inductance. If one coil is connected to a source of alternating voltage, an alternating flux is set up in the laminated core, most of which is linked with the other coil, in which it produces mutual induced EMF. So this way of production of mutual induced EMF creates induced EMF in the secondary turns. So this secondary turns will have an output of voltage E in the turns as well as the output of voltage V in the terminals, and this is being caused due to mutual principle. According to Faraday's law of electromagnetic induction, E is equal to m di by dt. Here m is the mutually induced flux and di by dt is the rate of change of current with respect to time which is present in the primary coil. So, if an alternating current is being applied in the primary coil and this current is being changed with respect to time, so induced EMF is being produced and this induced EMF is represented as E, and this is given by Faraday's law of electromagnetic induction. And this E is equal to m di by dt, where m is the mutual inductance created by the coil. If secondary coil circuit is closed, a current flows in it and so electric energy is transferred entirely magnetically from the first coil to the second coil. So if the second coil, that is the secondary, is being closed at this time, the magnetic energy which is present in the core and which is produced by the primary is converted into current in the secondary coil, and this secondary current will flow in the secondary circuit when the secondary terminals are closed with the help of a circuit. The first coil in which electric energy is fed from the AC supply mains is called primary winding, and the other from which the energy is drawn out is called a secondary winding. So if you connect a source to the coil, then this coil is known as primary, and if you gets an output from the other end of the coil, then it is known as secondary. So you can inversely use the transformer. This can be primary and this can be secondary. So the real meaning is, if you connect a source to a coil in a transformer, then it is primary, then that coil is primary, then the other end, that is the another coil, which is named as secondary. A transformer is a device that transfers electric power from one circuit to another. It does so without a change of frequency. So the electric power is transferred from primary to secondary, whereas the frequency is not being changed. It is accomplished by electromagnetic induction. Two electric circuits are in mutually inductive influence of each other. So, to transfer the electric power from one circuit to another in magnetical coupling, the two coils should be mutually inductive and influence with each other. Transformer construction. So, the single element of a transformer consists of two coils having mutually inductance and a laminated steel core. So you know that transformer has two coils, one is primary and another one is secondary, and these two coils are wound on a steel core. So this steel core is known as the laminated core, and these laminated cores are being used to avoid eddy current losses. The two coils are insulated from each other and the steel core is being placed. Other necessary parts are container for assembled core and the windings. So container is nothing but the core which is being used to assemble the complete setup. Medium of insulation insulating the core and its windings from its container. So the two coils are being kept in the single core, so these two coils should not touch each other. So to ensure this, the insulating windings are being present in an insulation medium. The insulation medium may be a paper, mica or oil. Suitable bushing, porcelain, oil-filled or capacitor types for insulating and bringing out the terminals of the windings from the tank. So to take the windings out, that is the two primary winding and the another two secondary windings are should be taken out from the transformer. To do that, suitable porcelain bushings with oil filled or capacitor type filled are being used. In all types of transformers, the core is constructed of transformer sheet steel laminations assembled to provide a continuous magnetic path with a minimum of air gap included. So, the complete transformer setup is being placed inside a core, and this core will be made up of steel laminations. Okay, the steel laminations are being used because the steel laminations will help us to avoid eddy current losses. The steel used is of high silicon content, sometimes heat treated to produce high permeability and a low hysteresis loss at the usual operating flux densities. So, the silicon steel is being used to make the core of a transformer, and these cores are being laminated. So sometimes these silicon steels are heat treated to produce a high permeability and very low hysteresis losses, so that the operating flux densities will be increased, whereas the losses due to magnetization is decreased. The eddy current loss is minimized by laminating the core, the laminations being insulated from each other by a light coat of core plate varnish or by an oxide layer on the surface. So, the laminations are being insulated with the help of varnish or mica or paper. So, in real transformers, these laminations are being insulated with the help of thick layer of varnish coating. In between the two laminations are joined together. Several such laminations are being constructed one by one, and they are assembled together and they are riveted to get a single core. The thickness of the laminations varies from 0.35 mm for a frequency of 50 Hz to 0.5 mm for a frequency of 25 Hz. So, each lamination thickness is being varied. For frequency of 50 Hz, the lamination thickness is 0.35, and for 25 Hz, the thickness of lamination is 0.5 mm. Constructionally, transformers are two general types, distinguished from each other by the manner in which primary and secondary coils are placed in a laminated core. So, these transformers are of two types. Okay, the transformer is of two types. Okay, this types is only depend on the constructional features of the transformer or how the winding is being arranged inside the core. There are two types of transformers. The first type is nothing but the core type, and this is the figure of the core type transformer. And the second one is the shell type transformer, and this one is the figure of shell type transformer. We will describe in details about core and shell type transformers. Here, this is the core of the transformers. The assembly of complete core of two types of transformer is shown in figure. Here, E-shaped lamination, L-shaped lamination, I-shaped laminations are being used, and these laminations are being connected or back to back to form the core. So, these are the L-shaped lamination. And in the L-shaped lamination, you can see the coils are wound like this, and at this two joints, this joint and this joint, they will use butt joints to make the core. To avoid high reluctance at the joints where laminations are butted against each other, alternate layers are stacked differentially to eliminate these joints. So, in this figure, you can see this is square type joints. Here, the butt joints are being eliminated because when we use butt joints, the reluctance present in the core is being increased, so that the flux is being flux is not able to pass through the butt joints as it is. So to avoid this, we are using this type of joints, and in this type of joints the butt type joints are being eliminated and the flux will pass very easily. Next we will be seeing about core type transformers. The coil used are form, wound and are of cylindrical type. So in a core type transformer, the windings are made up of cylindrical in nature. The general form of these coils may be circular or oval or rectangular. So the coils which are shown here are made of circular in nature or oval in nature. Sometimes it may be rectangular also. In small size core type transformers, a simple rectangular coil is used with cylindrical coils which are either circular or rectangular in form. Here you can see the core of the transformer, and these are the laminations present in the transformer, and this is the low voltage winding and this is the high voltage winding. These two windings are made up of copper, and these two windings are separated by the insulation which is present in between them. So the two coils which are touching together should be insulated with the help of varnish, whereas the low voltage and the high voltage windings are being insulated with the help of a thin paper or mica. In large size core type transformers, round or circular cylindrical coils are used which are so wound as to fit over a cruciform core section. The circular cylinder coils are used in most of the core type transformers because of their mechanical strength. So in major transformers, in major core type transformers, circular cores are being used. And this is the cross-sectional view of a core type transformer. This one is the core, and here is the winding. This one is the low voltage winding, and this one is the high voltage winding in the one limb. Similarly, in the other limb also you will be having low voltage and high voltage winding. Both these coils are being connected in parallel inside the transformer. Next we will be seeing about shell type transformers. The coils are form wound but are multi-layer disc type, usually wound in the form of pancakes. Here this is the shell type transformer. The only difference in these types of transformers, the coils are wound in the form of pancakes, whereas you can see this is the low voltage winding. Next there will be high voltage winding. Then here is the core. This one is the core. Okay. Next you will be having another high voltage winding and a low voltage winding in one limb. In the next limb also you will see the same thing. This is the low voltage winding, high voltage winding, and this is the other end of the core, and this one is the high voltage and low voltage winding. So this type of construction differs only from the winding and how the windings are being placed inside the core. So when the windings are placed like this, then it is known as a shell type transformer. The different layers of such multi-layer disc are insulated from each other by paper. So these discs are being insulated with the help of a paper. The complete winding consists of stacked disc with insulation space between the coil and the space forming horizontal cooling and insulating ducts. So when the transformer is being loaded at once, the heat will be generated in both the coils. So to remove the heat from the coils, the air ventilation should be made with the help of ducts. So horizontal cooling ducts and vertical cooling ducts will be present. In these cooling ducts, in large number of transformers, the oil is being used for cooling the transformer. In low power transformers, we will be using air as a cooling medium, but in high power transformers, we will be using oil, forced oil, or some other coolant can be also used to cool the transformers. Shell type transformers may have a simple rectangular form also. So this is the another figure for a shell type transformer. These transformers are being connected that in a pancake structure, so that each and every windings are wound. After the windings are being wound, they will be inserted into the core. First a low voltage winding, next a high voltage winding, next a high voltage winding, and the next a low voltage winding. Similarly, these pancake structures are being arranged like this, and the transformers are made. Next, we will be need to know about the ideal transformer. An ideal transformer is one which has no losses. That is, its winding has no ohmic resistance, there is no magnetic leakage, and hence which has no I square or core loss. So, uh, if you wound a coil, then the coil has some resistance in practical. Okay, if you wound a copper coil, then this copper coil will have some amount of resistance. Okay, this resistance will produce a drop, and this resistance will produce a I square or loss. So regarding electrical, these losses will be present. When you consider magnetic, there will be hysteresis loss in the material we are using in the magnetic material. But now in case these losses are neglected, so it is known as the ideal transformer. In nature, there is no material in such a way that which has a zero ohmic resistance. So there is no metal like that having no resistance. So for study purposes, we are using an ideal transformer to have a complete view of a transformer. So this is one such transformer. Here the voltage V1 is the applied voltage, and E1 is the induced EMF present inside the coils, and E2 is the induced EMF present in the secondary turns, and V2 is the output voltage from the secondary. Since it is an ideal transformer, you can say V1 will be equivalent to E1 and E2 will be equivalent to V2. At the same time, you can also say the power input present in V1 will be equivalent to the power output present in the V2. So both the powers fed in the primary as well as in the secondary will be the same. And this is the graph showing the voltage and current waveform present in both the circuits. And this is the phasor representation. Since there is no losses present in the transformer, the phasor diagram will be like this. V1 and V2, here similarly E1 and E2, and the currents will be as in the 90-degree phase shift. In other words, an ideal transformer consists of two purely inductive coils wound on a loss-free core. Okay, if you want such ideal transformer, you need to find a material which is very purely inductive and it should have no losses in the core. So such materials does not exist. It is impossible to realize such a transformer in practice because in nature each and every metal has a resistance. So such type of transformer, that is an ideal transformer, cannot be developed in practice. Step up and step down transformers. If primary coil has 3 loops and the secondary coil has 30 loops, then the voltage is stepped up by 10 times. Here you can see this one is the core of the transformer and this is the coil winding. You can see in the primary coil you will be having only 3 turns, whereas in the secondary coil you are having 30 turns. Then the transformation ratio, that is known as step up transformer, because this 3 turns is being stepped up to 30 turns. So the voltage you applied here, if you apply 1 volt over here, then you will get a 10 volt in the secondary coil. So this step up principle is being used in a step up transformer. Whereas in the step down transformer, the primary coil has 30 turns and the secondary coil has 3 turns. So if you apply 10 volt in the primary side, you will get only 1 volt in the secondary side. So both the transformers are same. So you can reverse the coils. Okay, if this transformer you reverse this secondary to primary and primary to secondary, then you will get a step down transformer. Okay, both the transformers are same. If you are connecting the primary winding to the source or secondary winding to the source, this makes the matter. Now we will going to see about the voltage equation of a transformer. Here N1 is the number of turns in the primary. You can see these are the turns, and N1 refers to the number of turns present in the primary, and N2 represents the number of turns present in the secondary. And so the magnetic flux pi m, that is the flux being produced by the primary, and this is the maximum flux which is present in the core, and this is being measured in Webers, and this pi m will be equivalent to Bm into A, where Bm is the flux density of the material, and the A is the cross-sectional area of the core. F is the frequency of AC input in Hertz. Here this is the AC supply, and you are going to apply an voltage V, and its frequency is being represented here, and this is the time axis and this is the voltage axis, and you know T is equal to 1 by F. Flux increases from its zero value to maximum value pi m in 1/4 of the cycle, that is 1 by 4 seconds. So the value of flux being the same as shown in the curve. Okay, the flux value will increase from 0 to its peak value within the 1/4 of the cycle, and it will get decreased to a zero value in the next quarter of the cycle, and in the next quarter of the cycle it will be in the negative magnitude of flux, and in the next quarter it will again comes back to zero value. So the average rate of change of flux can be represented as pi m divided by 1 by 4 f. So we will get 4 f pi m Webers per second or volt. Okay, now rate of change of flux per turn means induced EMF in volt. So the total induced EMF present in the primary, you can now say average EMF per turn is equal to 4 f pi m volt. So in a single turn of this coil, you will get an output voltage of 4 f pi m volt. If flux pi varies sinusoidally, then RMS value of induced EMF is obtained by multiplying the average value with the form factor. So you know form factor is equal to RMS value divided by average value, which is nothing but 1.11. So you need to multiply the form factor with the average EMF per turns. So the RMS value of EMF per turn. So if you consider this thing, in a single turn, you will get the RMS value, which is 1.11 into 4 f pi m, which will be equivalent to 4.44 f pi m volts. So the RMS value is 4.44 f pi m volts in a single turn of the transformer. Now the RMS value of the induced EMF in the whole primary winding, which can be found out by induced EMF per turn into number of primary turns. So since we have found for a single turn, you need to find for the complete number of turns present in the primary winding. You know that the number of primary windings which is represented as N1. So you just need to multiply N1 with this equation, which is nothing but 4.44 f N1 Bm A. Why Bm comes here is you can substitute pi m is equal to Bm into A. So you can use 4.44 f N1 Bm A by substituting pi m is equal to Bm A. Similarly, the RMS value of the EMF induced in the secondary is E2, and E2 is nothing but 4.44 f N2 pi m. Okay, similarly you can substitute pi m is equal to Vm into A, so 4.44 F N2 Bm into A. In an ideal transformer on no load, V1 will be equivalent to E1 and E2 will be equivalent to V2. So the input voltage V1 will be equivalent to E1 because the copper present in the winding or the coil windings are made of copper, and these copper windings have no losses because it is an ideal transformer. So you can assume this is a different metal, and this metal has no losses or copper loss present in it. So now you can assume V1 will be equivalent to E1 and E2 will be equivalent to V2. Next, we will be going to see about the transformation ratio. Here, the transformation ratio is represented by the symbol K. Okay, here is the K. The constant K is known as the voltage transformation ratio, and it is denoted by K is equal to N2 by N1 equivalent to E2 by E1 equivalent to I1 by I2. So this transformation ratio is very important in determining the step up or step down transformation ratio of a transformer. So if N2 is greater than N1, that is K will be greater than 1, then transformer is called a step up transformer. Whereas if N2 is less than N1 and K is less than 1, then transformer is known as step down transformer. Okay, if N1, that is this one is N1 and this is the N2. Okay, assume if N1 is lesser number of turns and N2 has more number of turns, then this transformer is known as a step up transformer. Similarly, if N1 has more number of turns and N2 has lesser number of turns, then it is known as a step down transformer. Again, for an ideal transformer input, VA is equal to output VA. So the rating of the transformer is represented in volt amperes, which is kilovolt amperes. These transformers are not rated in watts because the power is not being changed, only the voltage and current is being transformed. Because the voltage and current is only being transformed from one circuitry to another circuitry, the rating of the transformer is based on volt ampere. Now you can say V1 I1 is equal to V2 I2 because you know volt ampere VA and the output is also volt ampere. So V1 I1 will be equivalent to V2 I2. So you can say I2 by I1 is equal to V1 by V2, which is nothing but 1 by K. Thank you.